So now, let's do an example of finding. So we're going to find the velocity vector and the speed at t equals 3 seconds of a particle, so we have a little something here that's moving, whose position vector is the following formula. So we have r of t is equal to e to the t times I hat minus 2t squared times j hat, and then plus a 5t times k hat. Okay, so what we're going to do here is first of all find the velocity vector. So our velocity vector is going to be given by r prime of t, and that ends up just being a vector, right? So how we do this is we're going to take our x prime of t, that's going to be our first component, y prime of t, and z prime of t. Okay, and I'm going to go back to the top here and rewrite this in vector form just because I like vector notation. So this is going to be an e to the t, a negative 2t squared, and a 5t. Okay, so now all we have to do is take the derivative of each of these components separately. So what we're going to get is the following. So if we take the first derivative here, we get e to the, e to the t, okay? And then we get a negative 4t for the second component, and then simply a 5 for the last component there, okay? All right, so now let's see, what are we going to do here? So this is our velocity vector. This is the general formula for it, but we have to find it at t equals 3 seconds. So we're just going to simply plug in a 3 for the t spot. So then we get e to the 3, or e cubed, and then negative 4 times 3, so that'd be a negative 12, and then a 5. Okay, so we found the first part. This is the velocity vector evaluated at 3. Okay, so what is the speed? So for speed, that's going to be a scalar valued function, right? So v of t, like curly v of t, is equal to the magnitude of v of t, the vector v of t, okay? So for this, what we're going to do is actually plug in what we just found for the components of our velocity vector. So what we're going to do is square each of the components separately and then add them all together. Okay, take the sum, and then we have for the last one 5 squared, and then we're going to put them all under the square root sign. Okay, so we're going to continue from here. V of, and I should actually put 3, right, because we already plugged in a 3 for our t. That's how we got the velocity vector inside there that we are now taking the magnitude of. So we get an e to the 6th plus 144 plus 25, all under the square root sign. And finally, this simplifies to e to the 6th plus 169, all under the square root. Okay, so this is, the second value here is our speed at t equals 3 seconds. Okay. All right, so now for a pretty important topic called arc length. So again, we're dealing with arc length, but this time we're dealing with arc length parameterization. Okay, long word there. All right, so what is arc length parameterization? Basically, so what we want to do is, so here's the big idea, okay? So the big idea behind it is to find a parameterization, and I'll just abbreviate parameterization, so that the speed, and this is what we just learned, our v of t, okay, has a constant value of 1. Okay, 1's a pretty simple value there. So basically what we want is for our v of t, also known as magnitude of r prime of t, okay, to equal 1, and for all t. There we go, for all time. Okay, so and why are we gonna do this? Because we feel like it, kind of, because then this way, this is what happens. This is why this becomes so convenient later on. So then our distance traveled, so our arc length, right? So distance traveled, arc length of a path, that is, distance traveled on a path over some interval, AB, some t interval AB, is going to equal integral from a to b of r prime, magnitude of r prime of t, dt, right? And then, if we do have this arc length parameterization, that means that the magnitude of r prime of t is going to equal 1, right? So this is going to equal 1. So that means integral from a to b of 1 dt. So then we just get that this is equal to b minus a. I mean, how easy is that? So basically, the reasoning behind this is because it makes our lives easier. So that's always good. Yay. Alright, so now how do we find this arc length parameterization? Like, what are you even talking about? How are we going to make our lives easier? And I must admit that we have to go through a little bit of work in order to make the future, or problems that go further in the future, easier for us. So here are the steps to find an arc length parameterization. So steps to find arc length parameterization, ALP. Okay, ALP. Alright, so the first thing we're going to do is start with the given parameterization. And again, I'm just going to use an r arrow of t, okay? R arrow of t. What we're going to do is just form our arc length function. So s of t is equal to 0 to t of r prime, magnitude of r prime of u du. Okay, so this is our arc length function, and this is such that r of t does not equal 0 for all t. And this last condition here, that just means that we don't have the 0 function and it's not just staying at the origin, and that there actually will be some kind of length going on. So anyways, you don't have to worry about that second part. It's mainly just you're going to form your arc length function, okay? So that's the first step. And then what we're going to do, once we find this function, is we're going to find the inverse of it. So find inverse t of s, okay? AKA, sometimes the book and other like professors and stuff, they like to write this as g of s because it's technically another function. So anyways, so then it kind of just think of this as the same thing. I like to think of t of s because then I know, okay, so this is the function t in terms of s, so that should be the inverse of s of t, right? So anyways, so s of t and whatever you have, t of s, aka g of s, are inverses, okay? Inverses. Alright, so once you find this t of s, this function here, the third step is the final step. So 1, 2, 3, kind of nice, right? So finally, we're going to plug our, and I'll just say g of s, whatever function we get of s, equals t of s, into r of t, our original parameterization. So you're going to do this wherever you see a t. Wherever. Okay, how do we spell here? Wherever. Are there 2 E's in between there? Anyways. Okay, so wherever you see a t. C-A-T. Okay? So basically, what we're going to end up with is something that looks like, I'll show you on the next slide. So we're going to end up with a parameterization that looks like P of S, such that the magnitude of this P of S is always going to equal a 1. Okay, so now see how S is our new parameter. S equals our new parameter variable. Another way to write this, or to think about it, is this P of S is kind of like the same thing as R of T of S. Okay, we just kind of we stuck this S in here so that our overall parameterization, it now has now that we get a constant speed of 1. All right. Okay, so that pretty much does it for this video about arc length and speed. I hope that helps, and I'll talk to you in the practice problems video if you watch.